Okay, the concept of limit is a very important concept in differential calculus for starters. We're going to use limits later on to be able to determine what is the gradient of a line that is tangent to a curve at one point. It seems quite a simple concept, but it really isn't, because remember that for you to be able to calculate the gradient of a line, you need 2 points. So it's going to be interesting to see, and the only way in which we're going to define how to find the gradient of a line at a point is by using the concept of limit. So I'm going to start with a very simple function, the quadratic function, y equals x squared. And I'm going to have a look at see what is the value of the function, what value does this function approach as we approach the value of 2. Okay, I'm going to start from the left hand side, so going from 1 towards 2, increasing all the way to 2. And as I see the values go from 1 all the way, and let's see that I jump from 1 to 1.9 and then 1.99, and as you do that, you will see that the values of the function is actually getting bigger and bigger, but they're also getting bigger and bigger approaching a certain value. In this particular case, you could guess that when x is equal to 2, and obviously if you do substitute 2 over here, you will find that the value at 2 is 4. The same way, so we can say then that as x approaches 2 from the left, the function approaches the value of 4. Considering the same function now, but going from the right, in other words, from 3 going all the way down to 2, we can actually say the same thing. We say, well, as the function goes, or the value of x goes from 3 and gets closer and closer to 2, the value of my function goes down from 9 and approaches 4. So considering that, I could actually say that as this function approaches, as the value of x approaches 2 from both the left and the right, the function approaches the same value, the value 4. So we could then conclude and say that the limit of this function when x tends to 2 is equals to 4. So here is a second example. We have a function f of x equals 5x plus x squared over x, and we wish to find what is the limit as the x approaches 0. And please note that in this case we say as x approaches 0 simply because when x is equals to 0, this function doesn't work. You cannot simply substitute 0 in this function because you're going to end up with an error which says, or basically something that is meaningless or undefined, which is 0 over 0. So how do we go about finding that limit? Again, what we're going to do is we're going to check what happens to the value of this function as we approach 0 from the left and approaches 0 from the right, and that will give us exactly what the limit is. So the limit is always something that we should look at in 2 parts. Okay, so here is the function, and now what we're going to do is we're going to see what happens to the value of the function as we approach 0 from the left. The function will approach the value of 5. When you approach 0 from the right, the function will also approach the value of 5. But at 0, when x is equal to 0, the function really doesn't have a value. Okay, so we in this case will have to rely on the concept of limit for us to be able to get what that value might be. In this case, we can now say that even though the function doesn't exist at x equals to 0, the limit as x approaches 0 on this function is 5. Here I've got a function, one of the piece functions that I explained to you last week. And what I'm going to do is I want you to have a look at what happens to this function as I move this point C closer and closer to 0. So in other words, I'm going to approximate, and remember that last week we actually talked about this, what happens as my point C gets closer and closer to 0, and then I'm going to do the same with the point A. Now please keep an eye on the y-coordinate of these points, which is the value of the function. So what happens to the value of the functions as I approach 0? So I'm going to take the point C and I'm just going to bring it closer and closer to 0. And I want you to notice exactly what's happening to the function. See what the value of the function is getting towards. The value of the function is getting towards closer and closer to 0. As I approach 0, the value gets closer and closer to 0. At 0, however, what happens is you have a question mark. In other words, the function is undefined at 0. Okay? But what happens in the vicinity of 0? So what happens as I get closer and closer to 0? So here is a point minus 0,04, which is quite small. I can try and get one even smaller, minus 0,03. minus 0,02 and see what happens to the value of the function as I get close to that. I'm going to do the same thing on the other side now. So if I took the point A and I try the same thing, just have a look at here. This is the coordinate of the point B, which is a point on the function. So as the point A gets closer and closer to 0, what's happening to the value of the function is also getting smaller, and it's getting smaller and closer to also 0. At 0, however, again we have the same situation where we have a question mark, which means the function is undefined. But the moment I go away from there, then the function gets bigger, and as I come closer and closer to 0, the function gets smaller and smaller, and it gets closer to a value of the value of 0. So if I was to say what is the limit of this function as x approaches 0, from the left, okay, x, the limit is 0, and from the right the limit is also 0, which means that this function has a limit of 0 as x approaches 0. Here we have a second example. Now we have a function that is split in the following way. So if x is between 0 and 3, the function has the form of the absolute value of x minus 1. And then if the function is defined for values bigger than 3, in this case I define it between 3 and 5, then the function has a value of 4. Again, I'm just going to look at the limits from both sides. So I'm going to start by taking the point C and bringing it as close to 3 as possible. I want to check what's happening in the vicinity of 3. So I'm going to grab the point C and look at the coordinate of the point C over here. As I'm moving it closer and closer, what's the value of the function approaching? So as x gets closer and closer to 3, the function gets closer and closer to, okay, I will say the point 2, right? So if I even move it even further, I can just go and say, well, if I take it closer and closer to 2, they are 2.99, so very close to 3. The function has a value of 1.99, which will make me assume that at 3 the function will have a value of 2. However, because this function is a split function, what happens at 2 is that I have a question mark, or otherwise the function is not defined over there. That's why I couldn't get a value for 3. On the other side, however, if I take the point A and I bring it closer and closer to the point C, look at the function that is defined at the top here. I take the function and I just start moving the point A, and as you can see, because this is a constant function, the value at 3 is 4. Okay, so when I get closer and closer to 3, on the left hand side, the function has a value, or tends to have a value of 2. In other words, the limit on the left is equals to 2. And as I approximate the value of 3 from the right hand side, because of the nature of my function, the function has a value of 4. In this case, the function is defined at 3. So when the x is equals to 3, the function has a value of 4, and that's why the 3 is included in my solution over here. And that basically means that on the left hand side the limit is 2, on the right hand side the limit is 4, so I cannot say that this function is continuous because it has a jump discontinuity. In other words, the limit from the left and the limit from the right are different from each other. So algebraically, how does the concept of limit basically works? It works the following way. When you can substitute, when it is possible to substitute the value into the function and obtain a value, then you can simply do that. So let's say, for example, we have the function y equals x squared, and we want to find what is the limit of this function at x approaches 2. Because substituting 2 into the body of my function will not give me something that is undefined, such as 0 over 0, or 0 over infinity, or infinity over 0, or something to that extent, we can then simply go and substitute, and we can say then that it is sufficient evidence for me to say that as x approaches 2, the function will approach the value of 4, and we can conclude that the limit when x is equals to 2 of x squared is equals to 4. However, when it is not possible to substitute, like it is the case of the function that I showed you before and this function in this case, if x approaches 0 in this function and I try to substitute the x by 0, I will end up with a 0 over 0, which is not something that is that does exist. So how do I calculate the limit? Well, my first port of call here will be always to, first of all, take out a common factor and then factorize in order to find the solution to the function. So finding to factorization or factorizing the function will be the best way. I factorize, simplify the x, and I see that as I simplify this x's, what I've done now is I have removed that 0 over 0. Now when I have the function written as x plus 3, I can simply substitute the x by 0 and get the value of 3. So I could say that the limit of this function at x when x tends to 0 is 3. Here is another example, x squared minus 9 over x minus 3. Similarly, if I substituted the x by 3, I'm going to end up with a 0 over 0. So the first thing that I do is I factorize and try to simplify it. Okay, and since I can simplify it because x is different from 3, see the value of the limit that I'm trying to calculate is as x tends to 3, not the value at 3. We can then simplify these two and therefore calculate the limit. So when x tends to 3, the limit of this function or this function will have a limit of 6. So now that we've introduced the concept of limit, we are now going to move on to continuity and discontinuity. It is very important for us to be able to say when a function is continuous or not, so that we can determine that function can be differentiated or integrated at a later stage. So it is very, very important for us to use the concept of limit in order to determine what the continuity and discontinuity of a function is. So what is a continuous function? We say that a continuous function is a function that is predictable. Calculus fundis refer to a continuous function as a function that you can draw without lifting your pen. In other words, that function has no breaks in the graph, it has no holes or no jumps, and therefore we can say that the function is continuous. So a continuous function is a function that is predictable. So in this case, we will say that this function x squared minus 9 over x minus 3, which is a function that we've worked with in the previous example, has a discontinuity at 3. Why? Because at 3 the denominator becomes 0 and the value of the function becomes undefined. It is then reasonable for me to say that the function is continuous everywhere else because the graph seems to have no other gaps or jumps. So we can look at this continuity only at the value of x where x is equal to 3. Mind you, this is a special type of discontinuity which we are going to discuss in a moment. Now, how do we define this continuity? And here is where the limit, the concept of limit comes in very. So what is a function? What do we consider a function to be continuous at a point? First of all, we say that a function f of x is continuous at a point if each of the following condition is satisfied. And please, I emphasize, each of the following condition is satisfied. First of all, the function has to exist at that point. Second, the limit has to exist, and the third and most important condition is that the value of the function and the value of the limit at that point are exactly the same. Here we have a case of a function that is continuous, okay, because this function can be drawn without lifting the pen, first of all. Secondly, we can say that at the value of c, the function has a value and the limit at that value is exactly the same as the value of the function, so this function is continuous. Okay, so let's talk about types of discontinuity, and we're going to start with removing discontinuity first. Now, for a continuity or a function to have a removable discontinuity, we have to state that first of all the limit of the function has to exist. Remember that for a function to be continuous, the limit is one of the essential points. The limit has to exist and has a value. That's what this means, and it's finite. But the function at the point is not defined, so therefore the function is different from the limit. Okay, but in this case we can actually say that because the limit does exist, the function can be made continuous at that point. Okay, let's talk about the types of discontinuity now. We're going to start with the removable discontinuity, which is one of the most common ones that you're going to be seeing. And in this case, as you notice, if we look at this, and again analyzing the concept of limit, the value of this function as you approach c from the left is L, or the limit as we call it. The value of the function as you approach c from the right is also the limit, although the function doesn't have a value at c, because the limit from the left and the limit from the right are equal, which means that the function limit does exist. We can then say that this is a removable discontinuity. In other words, the function is a not continuous at C, but because the limit exists at C, we can then say that the function can be redefined and say that at C the function will have a value of L, or whatever the limit is in this case. And that is a case of a removable discontinuity. Another type of discontinuity that is removable as well is the case where the limit from the left and from the right are equal. In other words, the limit of the function does exist, but the function at the point has a totally different value. Again, we can remove this discontinuity and then conclude that the function, because it has a limit, it can be redefined as continuous at that point. Then we move to the jump discontinuity, and this is also another one as the one that we're going to see more often in split functions that the graph that we looked in the last lesson, last week. And in this case, as you can see, if I approach C from the left, the limit approaches a particular value, which is completely different from the value that the function will approach if you approach C from the right. So as you approach C from the right, the function approaches this value, which is totally different. Even though the function actually has that value at that point, because the limit from the left and the limit from the right are not equal, we can then conclude that this is a case of a jump discontinuity. In some cases, they also call it a step discontinuity. In this case, the function cannot be redefined, and we say that the function is discontinuous at the point C. This is the case. These are basically the two cases of discontinuity that we're going to be studying. There is another type of discontinuity, which is also we like to look at it as a jump discontinuity, and it is when we have a vertical asymptote. In this case, if my function approaches C, or the value of x approaches C from the left, the function tends to infinity. On the other hand, when the function approaches C, or the value of x approaches C from the right, the function also tends to infinity. This is one of those that we call the infinite discontinuity, and again, this cannot be redefined simply because the function at infinity doesn't have we don't have an exact value. Therefore, we just say that this is a case of a vertical asymptote.